So after we have learned about the sources of biosignals that are related to physiological phenomena, and then we learn how about sensors properties. Before that, we learn the principle of measurement, and what parameters are uh, required, and what parameters need to be observed during a measurement. Then how do we know, or how do we compare sensors to sensors? The performance of sensor. How do we assess their performance? To evaluate their performance. So now we start to discuss about each of the sensors type, that are used to do measurement, or to convert information from their original energy domain, and their original physical or information domain into electronics domain, into electrical information domain. And here we will classify the types of sensors based on the principle that they are used, that they are using, to convert the physical domains and information. So what type of electrical parameters do this are this physical domain information converted into? So we are going to classify them and explain them based on this information or energy domain. The first type, which is quite common and also quite widely used in the industry, and as well also in biomedical instrumentation, especially for measurement related to biomechanics, to detect biomechanical signal, is the resistance-based sensors. So in resistance-based sensor, the physical domain signal is converted into resistance change. Of course, we know since a microcontroller, microprocessor, as well as even analog electronics, they do not process information in the resistance domain, in the resistance, in the form of resistance. They have this resistance later has to be converted into voltage parameter, in the electrical energy domain. So then it means that usually when we use this resistance-based sensor, we need a secondary transducer, either, for example, voltage divider, or could also be Whetstone bridge, as what we have learned yesterday. Okay, so let's now try to discuss the principle of this resistance-based sensor, and then we are going to see or to look at the different types of resistance-based sensors and measurement, as well as see the application of this resistance-based sensor for biomedical measurement. So the principle of resistance-based sensor is basically come from the fact that in any conductors, the resistance will change due to the dimensional change of that conductor. So for example, as you know also from biomaterials course, if we have initially this conductive material has a length L, when a force is applied into it at its two axial axis, in the top and the bottom, then it will exert a force F, and the force F will be divided, if it is divided by the cross-sectional area A, it will become stress, sigma. Okay. So as you have learned, maybe from biomaterial, you have learned this. Then this sigma, since the every material has Young's modulus, solid material has Young's modulus, has Young's modulus, E, Young's modulus E, and we know that the stress will cause a strain. It will cause elongation, and the elongation is called as delta, the extension, and the strain is defined as this delta divided by the original length, the initial length. And the Young's modulus is defined as the sigma divided by epsilon. Okay? When a stress is applied to a material, then the material will extend or will be compressed depending on the direction of the force. And this extension and this force or the stress will create length extension. It means the dimension of or the shape of the material will change. The L becomes L plus delta L. The cross section also will change. The cross sectional area, if you pull the material, the cross sectional area will decrease, right? Due to the Poisson ratio. Remember in the biomaterials. So this dimensional change will affect the value of the resistance, since we know that the resistance is a function of the resistivity, which is the property of the material, times L, the length of the resistor divided by the cross-sectional area. So both L and A changes. So both L and A change, then it will create change to the resistor as well. And later we will see that depending on the material type, also the rho may also change. The resistivity may also change. Okay. So based on that, the resistance change and the relative resistance change to the initial resistance, the delta R over R, can be calculated using this formula, which of course you could also derive this. Yeah, but based on the original formula, R equals to L. The basic formula is, of course, R equals to rho L over A. Okay, so this is if what we pay attention to is the rho, the resistivity change. Okay, and if you have delta rho over rho, this is relative conductivity change of the resistance wire, and then times the epsilon, the strain, and the mu, the Poisson ratio of the resistance wire, and this will create resistance change delta R over R. So this is piezo resistivity effect. So in many metal, usually what changes is the length and the cross-sectional area. Yeah, the delta R will be caused by the length change or the cross-sectional area change. But in some material, like piezoresistive material, like polysilicon, for example, usually these materials are materials which has multiple grain, yeah, has a polycrystalline structure. So when you apply strain to it, you apply stress to it, the boundary, the distance between the boundary, between the grain boundary will change, which will create delta rho conductivity change. Okay. So the K here, the sensitivity coefficient, is defined as a variation of resistance value caused by a unit strain. So it means when epsilon equal 1, what will be the delta R over R as a function of delta rho over rho. So then, therefore, how does a strain gauge sensor look like? So for example, it could look like a bonded foil type like this. Usually, it is made from alloy, from alloy foil, yeah, metal alloy. Metal alloy foil here indicates that the shape is in the form of very thin film, like this. Yeah. So this is the metal alloy foil, metal alloy foil. This is, for example, is constantan. This type of metal alloy that is embedded or coated onto a thin polyamide or case epoxy backing. So polyamide itself is polymer, yeah, that will form the flexible substrate for the metal thin film. Then The polyimide can be attached using special glue to the structure. This one is the structure which you want to, whose strain you want to measure. Okay, so this is connected. For example, here it has four. It has two strain gauges that is then connected to these four cables. Besides, in the form of metal alloy foil coated onto a polyimide or epoxy substrate, strain gauge or strain sensors could also be in the form of thin film, where the material of the strain gauge itself is being coated using sputtering. This is made by sputtering. Sputtering is through very high through bombardment of the target material, the bombardment of the strain gauge material, and the strain gauge material is being coated onto a certain substrate. So this is this is for an example of strain gauge from palladium chromium alloy thin film. Palladium chromium is metal alloy, yeah, coated onto silicon nitride turbine blade. So in this case, then the strain gauge can measure the strain exerted in this structure of the silicon nitride turbine blade. Yeah. Another example, for example, platinum. Here, this one, platinum rhodium, platinum tin rhodium, platinum tin film thermocouple applied on the space shuttle main engine turbine blade. Thermocouple basically can also be considered as a resistance-based sensor, resistance thermal sensor. Yeah, it measures the thermal change, the temperature change from the resistance or voltage change. So by sputtering the thin film of the metal engagement directly onto a polysensing area like this one in the silicon nitride turbine blade, it will eliminate the instability caused by adhesive bonds. In the previous example here, using polyimide, so the sensor is made as a standalone sensor, then it is attached to the structure whose strain you would like to measure. Okay, and this attachment is made possible by usually by using adhesive, epoxy adhesive, which is cured either using heat or using UV, for example. And sometimes this epoxy is not stable. Yeah? It may, the structure of the epoxy may degrade, for example, when that attachment is exposed to light or exposed to UV light or exposed to thermal radiation or exposed to heat. Yeah. So when you immediately or you directly coat the strain gauge material onto the structure whose strain you want to measure, coating it using thin film, this will make a more stable thin film, more stable strain gauge structure on the surface of that material. Yeah, like here. But it is more difficult. Yeah, so in order to sputter, you have to put the straps as well as the target material, the strain gauge material, in a vacuum setting, yeah, such that when you bombard in this case, for example, the platinum chromium alloy, the atoms can easily jump or into the surface of this turbine blade. If the environment is not vacuum, then it cannot get into the surface of the turbine blade structure. Another type is what we call a semiconductor strain gauge. So this is made from semiconductor. It can be made using single crystalline, monocrystalline silicon in either N-type or P-type. It could also be made using polycrystalline silicon. You already know the difference, right, between polycrystalline and single crystalline from material course. So the semiconductor strain gauge can be formed as bonded or unbonded or integrated strain gauge unit. If it is integrated, it means it is made using the IC technology, microelectronics technology inside that structure, inside that electronics together. Usually with semiconductor strain gauge, it will have high gauge factor. Remember what is the definition of gauge factor. So yeah, I should explain here that in resistance-based strain gauge, yeah, so we have the epsilon, which is delta L over L0, and we have delta R over R. This is the response which we are measuring, delta R over R, or R minus R0 divided by R0. Okay, and when we plot the delta R over R as a function of epsilon, so this is delta R over R. Yeah, I explained it yesterday also. Epsilon equal to delta L over L0. When you plot it like this, the gradient here, which is basically sensitivity, right? Remember the definition of sensitivity. M here will be the gauge factor. Yeah, the gauge factor. Depending if you write it in English, in British English or American English, gauge factor. So GF here, if it is straight line like this, then can be calculated from delta R over R divided by delta L over the gradient, which indicates the sensitivity of that strain gauge. So in the case of semiconductor strain gauge, then it has very high gauge factor, as you could also see from the quiz problem yesterday, number 2. You look, there is a one category P type or N type semiconductor, right? You look again, the gauge factor is very high. And semiconductor strain gauge is suitable for dynamic measurement. However, the drawback is that it is more temperature sensitive. It is also sensitive towards temperature. So if a sensor has sensitivity towards several variable or several parameter, we call that sensor to have cross sensitivity. So cross we here. So this is cross sensitive towards temperature. Cross sensitivity. Okay. Oh, so how to handle that problem? And then what you do is usually you have another sensor, also the same type of sensor, the same material of sensor, but you put in a region of that structure which does not endure or does not is not inflicted by the same strain, but they are having the same temperature change, for example. Okay, so one sensor is sensitive towards the strain as well as sensitive towards temperature. The other sensor is put or attached on surface in that structure, which does not feel the strain, yeah, it does not sense the strain, but only sense temperature change in the environment. So in that case, then later you could subtract the response from the temperature only, measuring strain gauge with the response from the strain gauge that measure both strain and the temperature. So this is how we deal, one of the way, not the only way, but one of the way to handle or to solve cross sensitivity problem. Yeah, cross sensitivity. Why is it problem? Because of course, when you don't have that compensating system, when there is a resistance change, you do not really know whether that resistance change come from strain stimuli or from temperature stimuli. Okay, and semiconductor strain gauge is inherently more linear than metal strain gauges, but more sensitive, yeah, because it has higher gauge factor. So this is an example of a strain gauge made from semiconductor. And this is the semiconductor itself. It is bonded to electrodes, to this one. This is also the semiconductor material bonded to the electrode. So here you are measuring strain here using 2 strain gauges. It has 4 electrodes like this. Yeah, as I have mentioned just now that many of the strain gauges are also sensitive towards temperature. And this may cause error which we do not want. because then so the additional error caused by temperature change in the measuring circumstance. The cause is that strain gauge has this resistance temperature coefficient. It means they are sensitive towards temperature change. The value of their resistance varies also with temperature. Then another cause of error due to temperature may be due to the differences of the linear expansion coefficient of the tested pieces and resistance sensing material. So for example, if you have like this, it is usually has less thermal expansion coefficient because the material itself, the strain gauge material itself, the platinum chromium or the platinum rhodium platinum, is immediately coated onto the surface of the metal, onto the surface of the silicon nitride turbine blade. So they are really interacting. There are interface between the two materials. So therefore, then the difference between the thermal expansion coefficient may not be that significant. However, if you have it like this, you have the strain gauge material being coated on a polymer, which is a polymer. Then polymer itself is attached to the steel structure, this steel structure using epoxy, using glue. Okay? And the glue itself, of course, has different thermal expansion coefficient than the steel whose strain you want to measure. The glue has different thermal expansion coefficient, then the polymer itself has another different thermal expansion coefficient, and the alloy foil itself then has another different thermal expansion coefficient. So you have 4 different thermal expansion coefficients. This may cause errors due to the temperature because each will expand at different extension. You know the meaning, yeah, of thermal expansion coefficient. So if thermal expansion coefficient means that how far that the structure of material will elongate when there is a temperature change. So delta L equals to L0 alpha T. Yeah, so L will be equals to L0 1 plus alpha T. Here the thermal expansion coefficient indicated by alpha. The alpha for different materials, of course, will be different, even when they are of the same metal. For example, the same metal type of material, they will have different thermal expansion coefficient. Let's say between iron and copper. Let alone if, like this, in this case, there is a polymer, polyamide. There is also polymer, the epoxy, and then you have 2 different metal. The steel, in this case, yeah, in the bottom part, with whose strain you want to measure, and you have the alloy foil. Okay, so when temperature change, for example, due to heating at during the noon, then the steel may expand differently compared to the metal foil. And this can cause error due to the temperature. Then we have also the resistant temperature coefficient. Yeah, I have explained. And then how to solve this problem of errors due to the temperatures. The first one is using 2-wire connection like this. Okay. So in 2-wire connection, this is basically the whetstone bridge configuration. Only at the arm of the bridge where the resistor is being connected, we have this additional resistors due to the wire, RL and RL, because this, like this, if you see this one, this is then connected to wire. This is also then connected to wire. So you see here, then the wires connect the sensor, which is here, whose resistance will vary with strain, indicated by this R0 plus delta R. Okay. Then we have other 3 resistors in the arms of the bridge. Then another way is you have 3-wire connection to that strain gauge. Yeah, so you make a parallel between this RL2 and RL3. Yeah, they are connected at one end of this strain gauge. The other ends are connected to the R3. Okay. So this is called quarter bridge circuit. Why? Because the sensor only occupies one arm from the four arms of the bridge. That's why it is called quarter bridge circuit. Basically, it is start of secondary transducer that will convert resistance change into voltage change here. So from R0, from delta R, yeah, from delta R, it is converted to V output, yeah, delta V output. In an ideal Whetstone bridge, when delta R equal to 0, then V output should be 0. Okay, V output should be 0. So V output is a function of delta R. We could also have half bridge completion. Half bridge completion is when the two arms of the Whetstone bridge are attached to strain gauges. For example, here, then this is connected to strain gauge 1, then another arm is connected to strain gauge 2. Yeah. So then the output of this Whetstone bridge, yeah, one is connected to the non-inverting input terminal of the op-amp. The other one is to the inverting terminal of the op-amp. So this op-amp will amplify the voltage difference between these two voltage divider, R1, R2, and this RG, RG. Okay. So R1, R2 are reference resistors. And another measurement error that may occur during measurement using strain gauge is when you put the strain gauge far away from the bridge. Okay, far away from the bridge, then an error may occur due to this lead wire that connects the bridge with the sensor. Yeah, because of course, ideally the lead wire should have zero resistance and 0 ohm resistance. But in reality, it is never 0. In reality, the wire will also have several ohms of resistance. So when we excite here an excitation voltage for compensation for the lead losses, okay. So the input, the output, yeah, the output of the bridge is tapped at this terminal AI plus and AI minus. Then you put reference voltage at the bridge here, RS plus and RS minus. Then, for example, you have one of the sensor here, either 1 or 2, for example. Then this bridge is connected far away from the excitation, from the reference voltage RS, in order that you compensate for the the lead wire, you put this excitation voltage, yeah, to compensate the lead losses. So that then, ideally, when there is no stimuli, the AI plus and AI minus difference will be 0. AI plus minus AI minus equals to 0, which we call as the null or null balance condition. So the other two arms with the same resistance must be guaranteed. Okay. This one. The other two arms with the resistance must be guaranteed. Working gauge and the compensation must have the same resistor temperature coefficient. Yeah, the coefficient of resistance change due to temperature change. They also have to have the same linear expansion coefficient, alpha, the same gauge factor, strain sensitivity coefficient, as well as the same initial resistance R0. The material used to paste compensation gauge and working gauge must be the same and with the same linear expansion coefficient. For example, if you use glue to attach Yeah, you paste to attach the gauge, the compensation gauge. Yeah, with the working gauge, the working sensor gauge must be the same as well. The two strain gauges must be in the same temperature field, so that then the here, if the temperature resistance here change to the temperature, the other in the opposite arm resistor will also change due to the temperature, and then the two changes will cancel each other. That is why they need to be put in the same temperature field. How to do self-compensation? So where if alpha 0 is the temperature coefficient, and we have the sensitivity coefficient here, the gauge factor K0 here, and the temperature coefficient should be equal to the minus K0 times the difference between beta G and beta S, where beta G, beta S are the linear expansion coefficient of the gauge and the reference. Yeah, the reference. Okay, where do we use strain gauge or resistance-based sensor in biomedical application? One of the examples, for example, here we can use strain gauge to measure blood pressure, but we need to have to install the strain gauge because it cannot directly measure the pressure. The pressure has to be converted first into deflection of a diaphragm. Yeah, when a diaphragm, a membrane, deflect, then you will have regions within the surface of the diaphragm that will be stretched. Some regions are being stretched, some regions are being compressed. Then you could put the appropriate strain gauge in these different regions of the diaphragm, which will detect the deflection of the diaphragm as delta R, resistance change. And then the resistance change could further be converted into voltage change using Whetstone bridge secondary transducer. The device itself, then the diaphragm can be put here inside this tubing, yeah, which is connected to the inner to the vessel, yeah, the blood vessel, using this saline filled non-compressible tubing that is being inserted to the artery, the blood vessel, using this needle. So the saline filled liquid will pass on the pressure from the blood vessel. Yeah, so that then this will be detected in the pressure transducer here. Yeah, that then the value of the resistance change can be indicated in the monitor. Okay, so this is how it looks like in actual picture. So this is the transducer. This is connected to the hot rigid pressure tubing. Usually it is made from polyurethane. Then this tubing is connected to arterial cannula to be inserted into the blood vessel. Okay, so let's see how it works. I hope you can hear the sound. Yeah?
Transducers in Invasive Pressure Monitoring by Dr. James DiNardo.
Hi, my name is Jim DiNardo. I'm a professor of anesthesia at Harvard Medical School and one of the cardiac ICU attendings here at Children's Hospital Boston. Today I'm going to be talking about invasive monitoring, specifically arterial pressure monitoring and central venous pressure monitoring. We're going to spend a little bit of time talking about transducers and how they work.
Transducers.
Transducers are a system that converts a mechanical signal, which in this case, in the case of pressure monitoring, both for arterial lines and central venous pressure lines, is a pulsatile signal, and it's converted through the transducer and then through this cable, converted to a digital signal, a pressure waveform, which is what you see on the monitor. And we're not going to spend a lot of time talking about electronically how that works, but suffice it to say that in order for a transducer to work, it has to be connected by a continuous column of fluid to the fluid in the patient's body in the system that you're monitoring, ideally with no bubbles in it, because as we'll talk about, the presence of bubbles in the transducer system degrades the conversion of the pressure signal to the electronic signal that we see on the monitor by damping out the pulses in the system. So we have this continuous volume of fluid, and we have the transducer generally hooked to a flush system. In this case, this is normal saline with a little bit of heparin added, running at about 3 mLs an hour, which is pretty typical. And that may vary
So heparin
from institution to institution. That's just a volume of fluid.
Heparin is usually used to prevent blood clotting, to prevent blood clotting, so to make the blood still in liquid form. That's why it is connected here in normal saline and heparin.
But necessary to keep the system free of clot and to prevent any thrombus forming on the ends of the catheters, which will also degrade the quality of the system and obviously creates a potential risk to the patient.
Zeroing the transducer.
When you zero a transducer, basically what you're doing is telling the transducer system and subsequently the monitor that the pressure being sent to the transducer is basically atmospheric pressure. So
so in Whetstone bridge, this is usually done by zeroing the V output between the 4 arms of the bridge. That's why usually in the reference arm, you put a potentiometer, so that then at the initial condition, when there is no stimuli, you tune that potentiometer such that then the output of the Whetstone bridge is 0. In this particular case that the doctor is mentioning, that the calibration is done against the atmospheric pressure. So the 0 in this sensor means that when the pressure, the blood pressure, is the same as the atmospheric pressure, at 1 atmosphere, or 10 to the power of 5 Pascal.
The way that's typically done is that we take the transducer and we turn the stopcock off towards the patient so that the only pressure the transducer is seeing now is atmospheric pressure.
So when it is like this, now that then this tubing or this channel or whatever is connected directly to the air, the atmospheric air. So the pressure at this transducer, which is basically here there is a membrane, is then the same as the atmospheric pressure. This is what we call zeroing this transducer.
That's the circumstance under which we zero a transducer. That tells the transducer to discount any other pressure except the atmospheric pressure in the room. And ideally, the transducer would be here.
So when in this condition,
it's the circumstance under which we zero a transducer. That tells
after it is being closed,
the transducer to
and the valve is being
except the atmospheric
switched on like this. So like this, then the blood pressure will be exposed. The membrane here will be exposed to the blood pressure. So it will measure the pressure of the blood relative to the atmospheric pressure that it has been calibrated earlier.
And ideally, the transducer would be here at the level of the patient's heart or near the level of the patient's heart. So
yeah, the transducer, it is
once the
important to put
transducer is zero,
the transducer at the same height or the same level as the heart. Yeah, because when you put it underneath, there will be an offset. If you put it more than it, there will also be offset, or positive or negative offset. So if it is at the level of the heart, we know that it is actually representing the pressure of the blood pumped by the heart.
we now have this continuous column of fluid from the patient vessel, in this case the artery, to the transducer. And as a consequence of that, we would get a reliable trace here of the arterial blood pressure.
Importance of placement.
The other important thing to keep in mind is that once the transducer is appropriately zeroed to atmosphere, where it lies relative to the patient will influence the pressure that we see on the screen. So, for example, we know exactly how much pressure a column of saline exerts in terms of millimeters of mercury. So 1 centimeter of water is equivalent to about 0.8 millimeters of mercury. And just keep that number in mind, because what that means is that if I had zeroed this transducer and I take it and I drop it down below the patient's arterial blood pressure is going to rise in millimeters of mercury. And that is both the systolic and
this
the
is because
diastolic and the mean blood pressure
hydrostatic
by an
pressure
amount equal to the weight, if you will.
Because of the hydrostatic pressure of the column of the fluid of the saline, because now the transducer is put below this level of the hand.
Of this column of fluid. So if I take the transducer and I drop it 5 inches below the patient, that's equal to about 9 millimeters of mercury of pressure. So this transducer now, which was 0 to atmosphere, is now seeing the patient's arterial pressure plus the weight of this column of fluid 9 or 5 inches or so below the patient. And obviously, if I lower it even further, I'm going to increase the weight of this column of fluid, then the pressure is going to be even higher. By the same token, if I take the transducer and put it up here, I'm now going to lower the patient's arterial pressure by a quantity equal to this column of fluid again, but in the other direction. So the point being that the patient's arterial pressure now, to reach the transducer, has to overcome the pressure loss generated by raising the height of the transducer. And in this case, if I raise it up 5 or so inches, I'm going to lower the patient's arterial blood pressure by about 9 or so millimeters of mercury. Now, with an A-line, that might not be so important. I mean, if your arterial blood pressure is 100 and I drop the transducer on the floor, I may raise your arterial blood pressure by, say, 15 or 20 millimeters of mercury, which is substantial, but not a huge amount. Where it becomes more important is the central venous pressure transducer. If I'm dealing with a pressure of 9 millimeters of mercury and the transducer is down below the patient that same distance, and I add 9 millimeters of mercury now to the number I'm seeing here, in essence, I've increased the patient's CVP erroneously by 100%. The point being that the position of a transducer is important in both instances, but when you're measuring pressure in low pressure systems, such as the CVP, it really makes an enormous difference. And if you're using the CVP to make clinical decisions, there's a big difference between a CVP of 9 and a CVP of 18. So it's important to remember that if I had zeroed this transducer and I take it and I...
Okay, I think we'll put it like the... So this is also important. It shows how important it is that the not only the sensor itself is important, but how we do the measurement is also important. How we insert the sensor into the measured system is also important. Okay. Here's another application where we use bladder resistance-based sensor to measure bladder volume for patients with urinary dysfunction. Usually in traditional ways to measure bladder volume is using pressure sensor or ultrasound measurement or bioelectric impedance measurement. However, there is usually potential defects or unwanted interference. The solution is to use implantable polypyrrole-based strain sensor. Okay, so this is an example of how usually the bladder volume is being measured. This is using
a curved or phased array transducer with an abdomen exam type is used to perform a transabdominal examination of bladder volume. The patient is placed in a supine position. It is helpful for the patient to have a sufficiently full bladder to identify each wall of the bladder. The transducer is placed in a longitudinal orientation in the midline at the level of the symphysis pubis. The orientation marker is directed towards the patient's thickness of the bladder wall.
So, like this, using this,
Power
then
Doppler can be used to
from the image, the doctor can predict, can estimate the volume of the bladder. But one innovative way by using resistance-based sensor is like this, using polypyrrole wire as the strain gauge put onto polymer substrate, which is then used to cover the bladder. The bladder covered by stock with strip lines of polypyrrole. Okay. Then actually this is also has been used for heart failure problem to measure the heart volume. And the circuit that can measure this reading, to read the output of the sensor, is shown here in this figure. And this is the sensing resistor, and it is put into this operational amplifier, basically a current amplifier, and connected to a Schmidt trigger to trigger the digital system that will then transmit the reading result. Okay, due to time, I will stop it here. It's this one at the